Yes. Okay, we're going to talk about muscles, how muscles contract, muscle fibers, and we're going to talk on the very small level, and then we're going to get a little bigger and talk about that, and then we're going to talk about the nerve coming down, touching the muscle, and stimulating the muscle contraction, okay? But we're going to the very small first, okay? Right? Now, we have muscle fibers, okay? We have some thick muscle fibers, right? Those are the myosin fibers. We have some, they're red for the myosin. That's why meat is red. Then we have some thin muscle fibers, okay? And the thin muscle fibers are not as thick, are not as strong, and they have a little divot in them here, 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 and such. Now, these are called myosin, M-Y-O-S-I-N, myosin fibers, and these are the actin, A-C-T-I-N. Those are thin, and the others are the thick fibers, right? Okay, now, right, along in here, we will have a protein called troponin, T-R-O-P-O-N-I-N, okay? Okay. We have another protein, kind of like a string, called tropomyosin. Tropomyosin. Okay? Now, what I did not draw, because I'm not a good artist, is these thin fibers, these proteins, these thin fibers, they're twisted like a double helix, like the DNA molecule, okay? But I can't really draw that very well, okay? But what happens is this, when we have a muscle contraction. This troponin, in the presence of calcium, right? In the presence of calcium, yes, this troponin changes its shape. And when it changes its shape, this tropomyosin covers these binding sites, okay? These binding sites are covered, right? Okay? And so what happens is, in the presence of calcium, and we'll talk about where the calcium comes from in a minute, those binding sites, you don't have to draw this, there's a lovely graphic in your book. And would you tell me what the name of that is? Figure?
9.3.
9.3, okay? Right? But anyway, what happens is in the presence of calcium, troponin changes its shape. And when it changes its shape, it pulls the tropomyosin out of the way. When the tropomyosin is pulled out of the way, guess what? All these binding sites are uncovered. Okay? Again, this is the thin filament, the actin filaments. Now, we have groups of myosin heads sticking out from the thick myosin, right? Those heads, when this is uncovered, it allows these myosin heads to attach and form what are called cross bridges, right? Okay, there's one more on the bottom. Let me turn my page here. Okay, there's another filament, and those are, is it elastic or elastin? Yeah, elastic. E-L-A-S-T-I. Those are elastic fibers, and they're made out of a protein called titin, okay? Right? And these keep these fibers pulled taut, right? These elastic fibers, right? When you're a kid, you had a trampoline. A lot of kids did, right? And all the way around the trampoline, right, you got springs, and the springs have one job, really more than one, but anyway, they keep the mat tight, right? Yes? That's what this elastic filaments do, fibers do. They keep the myosin tight, okay? So, in the presence of calcium, what's going to happen is these myosin heads are going to bind the thick and the thin filaments, are going to form a cross bridge, right? And again, calcium causes troponin to change its shape and the tropomyosin to move out of the way. Tropomyosin is like a string that covers, okay? Right? And so, how does that happen? How does this bind to that? They're very close together, and what happens is this. It takes adenosine triphosphate, ATP, for a muscle contraction, right? And we burn ATP to make muscle contraction so we can run or do whatever, right? But what happens is this. These myosin heads are normally shaped like this. Okay? And what happens is ATP, once the circle goes round and around, you got to start somewhere on the circle, so let's start here, okay? What happens is if they're already attached, ATP will bind here to the myosin head. When that happens, the cross bridge will separate, okay? The second step is that the ATP will split one of the phosphates off. So therefore, these heads, they're like spring-loaded. They will cock up for a split second, and then they do this, basically. Okay? When that ATP is split, right? And so what will happen is, as the two attach and form cross bridges, here, another ATP is split, here, 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 here. And these myosin heads will attach, click, 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 right? And form a cross bridge, which is very strong. I always like to bring this, if you folks know what these are. Right? Right? Yes? Notice, it goes click, and it becomes tight, right? Each time. Trying to get it to go one click at a time. Click, 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 click. Right? Those myosin heads go click, 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 click. Right? That forms the attachment. Right? Most of the time muscles shorten. Not always. We're going to talk about that in a moment. But most of the time muscles shorten. So that's what makes the muscle filament shorten. When this muscle shortens, guess what happens? I've got my elbow, right? Because this is shortening. The distance from here to here becomes shorter. The muscle is pulling, right? And that happens because those cross bridges are going and shortening, right? Okay? And such. Okay. Again, one more time. We have the myosin, the thick filaments. They're tied down by the elastic filaments that hold it tight. We have the thin filaments, the titin, the actin filaments. They're thin. ATP attaches here, separates, then the ATP splits. It cocks the mechanism. When the mechanism is cocked, it is the high energy state. It will attach to one of these divots in the protein here, and it will shorten, just like that, okay? And again, what starts it all? Calcium, right? Calcium. And what does the calcium do? It causes the troponin to change its shape. When the troponin changes its shape, it opens the binding sites. When the binding sites are open, then you can get the cross-bridge attachment. Okay? Now, not all of the myosin heads are attached at the same time, maybe half of them. Okay? Maybe half of them are attached at one point. All right? Okay. Now, that is minutely what happens. Yes? Now, let's go a little bigger. Where's the calcium come from? Where's the calcium come from? Right? If we look larger, we look at a bunch of muscle cells, right? Then what happens is that we have a plumbing system. Okay? We have a plumbing system. And this is called the triad, T-R-I-A-D, and that is the T-tubule. And these are terminal, T-E-R-M-I-N-A-L, terminal cisterns. Terminal cisterns, okay? It's called the triad collectively, right? Now, the way I like to explain that is this. Yes, if you live in the city, right? We have water towers and we have big water tanks, right? And then we have pipes running from those water tanks, and the pipes run down the street, many times under the street, in the middle of the street where I live on the main street, right? And then somewhere along the line, boom, we have a little pipe that splits off to each house, right? Yes? It's a plumbing system. It's a water system, right? Well, this is the system, the same thing, only calcium is in here. And the calcium is released, right? Is released, causing the tropomyosin to change its shape, causing the troponin to change its shape, right? I'm going to write that. Changes shape, right? Causing the tropomyosin to get out of the way, okay? And so, change my page here. Okay. This is around all muscle cells, and it is called the sarcoplasmic reticulum, right? And when we get down to individual cells, we call it the triad, the T-tubules and the terminal cisterns. And the calcium is in here, right? And it is released, right? When the calcium is released, the intracellular calcium goes up, troponin changes its shape, tropomyosin gets out of the way, ATP provides the chemical energy that becomes mechanical energy, and the cross bridges are formed, and you get a muscle contraction. Okay? Now, well, what stimulates that? Why does the calcium come out? Okay, we're getting to the bigger level. Yes? We're getting to the bigger level. Okay? Here we go right here. Okay? Again, let me look at my picture to make sure I get it exactly right. Okay? Here we go. Here we go. Right? This is the end of a nerve. Right? This is the end of a somatic nerve. Soma means body, somatic nerve. Okay? So, this is the end of the nerve. I'm not going to draw the other two. This is the end plate, the neural end plate, or the neuromuscular junction. Okay? Neural end plate. Also known as neuromuscular junction. Okay? So basically what happens is this. Right? A signal comes down that nerve, an electrical signal, right? And we're going to talk 4 chapters in neurology after this pretty quick, okay? We're going to talk more about that. But anyway, an electrical signal comes down this nerve, okay? Where the nerve comes almost, does not touch, but almost touches the synapse between the nerve and the muscle cell, right? What happens is that electrical charge that comes down the nerve opens channels in the very end of the nerve, right? The axon we're talking about. This is an axon, A-X-O-N. Remember dendrites, axons, right? Okay? So when this electrical potential comes down, basically an electrical charge comes down to the nerve, it opens calcium channels. Okay, so what happens is that calcium goes literally into the nerve, the end of the nerve there, right? Through these calcium channels. And these calcium channels are voltage regulated, okay? Well, what in the heck does that mean? That means this. It takes electricity to get them open, right? Now, I like to explain it this way. I have a garage door open. I push the button, electricity goes to the garage door opener, and the garage door opens, right? It only opens when the electricity hits it, yes? Okay. These calcium channels here, they open when the electricity hits it. They are called voltage gated, right? It's a gate. What's it take to get the gate to open? Electricity. They're voltage gated. So what happens is, when electricity comes down the end of this nerve, it opens the calcium channels. Calcium flows in, right? And when the calcium flows in, guess what? You have vesicles, little containers of a chemical, actually a neurotransmitter called acetylcholine. A-C-E-T-Y-L-C-H-O-L-I-N-E. Acetylcholine is the neurotransmitter for skeletal muscle. It's the very first neurotransmitter that we discovered, okay? When acetylcholine comes across, right? When the calcium comes in, the acetylcholine is released. The acetylcholine comes across the synapse, right, and comes in contact with the sodium and the potassium channels. Okay? Okay? Acetylcholine will come across and attach at the calcium channel, at the sodium and potassium channels. They're like a key that unlocks the door. And so that acetylcholine causes the sodium and the potassium channels, right? Now remember how we talked about cells are polarized, okay? Plus on the outside, minus on the inside. Remember? Here's a cell. You got a bunch of sodium out here, and you got a bunch of potassium in here, right? Because you have a bunch more sodium out here than in here, you have more potassium in here than there, right? The cell is positive on the outside and negative on the inside, right? Normally, most cells, it's about minus 90 to minus 110 or so, okay? Now, I have a meter, right? I have a multimeter, and I take that meter and I touch it to both ends of the battery, right? And it'll tell me, is my battery run down, right? It's a multimeter, yes. It'll tell me the voltage, right? A little AA battery is about 1.5 volts, right? So I will touch it, one to the plus, one to the minus, and I will read how many volts it is, yes? In the same way, if you were to take a multimeter, stick one end out here and one end out here, you would get minus 90 microvolts. It's not volts, it's microbyte volts, okay? So what happens is, when the acetylcholine comes across, the sodium channels are opened, and sodium, remember sodium is positively charged, but it comes flowing in. A split second later, the potassium channels open and the potassium flows out. If you measure the voltage, which they have, it will start at, let's say it was minus 90, okay? Then it'll go minus 80, minus 70, minus 60, all the way up to 0, plus 10, plus 20, about plus 30 is how far it goes. So what happens is, these two charges reverse. When they start out, they are polarized, P-O-L-A-R-I-Z-E-D, right? Plus out here, minus out here, yes? After those sodium channels are opened, and the sodium flows into that cell there, then what happens is it goes from minus 90, minus 80, minus 70, minus 60 to 0, not polarized, okay, to plus 10, plus 20, plus 30, okay? It is said to depolarize. This is polarized, and over here is depolarized, yes? And what happens is that in this synapse here, you have an enzyme called acetylcholine esterase, right? And acetylcholine esterase breaks down the acetylcholine. And when the acetylcholine is broken down, guess what? These channels close, right? Sodium stops flowing in. Potassium, it lags behind a few milliseconds, will stop flowing out, and you will go from 30 to 20 to 10 to 0 to minus, 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 back to minus 90. It is said to be repolarized, okay? Again, from minus 90 all the way to plus 30, the channel's closed, and it repolarizes back to minus 90. So it is said to be polarized, it is depolarized, and then when it comes back, it is repolarized. Right? And so what happens is that will start the muscle contraction. It's the calcium. Right? And so remember in the very first chapter we talked about the sodium potassium pump. Our body is working 24/7 to keep the right amount of sodium out and the right amount of potassium in, to keep this polarized about minus 90. Okay? right? That is its resting state. It's resting, right? But then when that shot of electricity comes down the nerve, it goes from being polarized to being depolarized to being repolarized, okay? Right? And that will spread from one muscle cell to the next. Okay? Excitation, something coupling, right? And so when that spreads, more and more muscle cells will be stimulated and more muscle cells will contract, right? And so, anyway, that's the way it works. I know it's kind of complicated when you think about it. It is, right? Okay? But again, let's start at the base, right? The muscle fibers. Yes? You got your actin, you got your myosin, you got your actin fibers. Calcium, right? Calcium from the sarcoplasmic reticulum. Calcium is released, makes a troponin change its shape. The tropomyosin is pulled out of the way. ATP attaches here. You get your working stroke. Every time one of those potassiums, phosphates, pardon me, one of those phosphates is knocked off, then you get, and generally the muscle is going to shorten, right? Oh, by the way, actually the muscle can lengthen too. If you're running up a hill, your calves are really contracting, but they're getting longer. We're going to talk about that in a minute, right? So it can shorten, but it can lengthen technically. But most 90% of the time, we're talking about them muscle shortening, okay? Right? And again, where did the calcium came from? The calcium came out of the T-tubules in the terminal cistern. It's just a plumbing system that has calcium in it, right? And we also have a calcium pump that after the calcium is out for a split second, it gets pumped right back into the cistern, right? Are you familiar with the term cistern? Do you know what a cistern is? Right? In Argentina, no, pardon me, in Chile first I saw this, right? On top of the house, they'd have a big, round, huge, like barrel, right? And when the rain would rain on top of the house, it would get collected in the barrel. Yes? It's a cistern. That's what a cistern is, right? And so when you want some water, you go to the faucet and you open the faucet, and gravity, it's on the roof. And it runs down through the pipes and you get your drink of water and you turn it off from the cistern, right? In the same way, these are cisterns, only they hold calcium. Okay? In the same way. Have you been to South America? No? Yes? They do that in Mexico too? Okay. They do that in Mexico too, right? They have cisterns, right? Yes? Uh-huh. Okay. Anyway, that's what a cistern is. Yeah? Okay. Now, what starts this is an action potential. An action potential is a fancy way of saying electricity running down the nerve, right? Okay? And we're going to talk a whole bunch about that in future, 4 more chapters of that, okay? But anyway, when that electricity runs down that nerve, there are voltage-gated channels. What is calcium channels? What is voltage-gated? Voltage means you got to have electricity, and when the electricity's there, they open up, right? If the electricity goes off at your house, you can push all you want to on that garage door opener. Is the garage door opening? No electricity, right? Yes, it's voltage gated. Got to have voltage to make it go up. The same way, these channels, right? When they're stimulated, electricity opens these, right? Voltage gated, okay? Now, the calcium goes into the end of the nerve. In the very end of the nerve, we have acetylcholine. Acetylcholine, the first neurotransmitter we discovered in skeletal muscle. There are many other neurotransmitters, but acetylcholine is the most common one, okay? That acetylcholine is stored in vesicles, little buckets, and it will be released through exocytosis into the synapse. It will go across the synapse and cause the the sodium channels to open first. Sodium channels open, and remember it's already charged about minus 90 to the inside, positive to the outside, but the balance between the two is about minus 90. And when that happens, sodium goes flowing in, and when sodium goes flowing in, in a split second, this opens and potassium goes flowing out. The potassium is what causes this cycle of repolarization. But anyway, right? Yes? It's Red Rover with sodium and potassium. That's what it is, right? You play Red Rover, right? Red Rover, let so-and-so come over, and they run over here, and then a kid from over here runs over there. It's the same deal, right? Okay? So when that sodium goes across, it changes the voltage because you have sodium's positively charged and a whole bunch runs in here. So this minus 90, this plus and this minus switch, and that is said to be depolarized, and it goes up to about plus 30. But then acetylcholine esterase in the synapse, or synapse if you're British, acetylcholine esterase, ACE means it's an enzyme, it's an enzyme. Okay, so when that happens, the acetylcholine is broken down and it stops, and that causes the calcium channels to close. The potassium channels are still open, the potassium is going to run out. And then your body is going to work to reestablish through the sodium potassium pump to reestablish that charge. Okay, so it goes round and round and round. Okay, we're talking split seconds, microseconds, okay? It's very quick, yes? But that is the way it happens, okay? And again, we're going to talk a whole bunch about how electrical signal running down the nerve later, okay? Right? But, sorry, it's a little complicated, okay? But that's what happens. We are run on electricity, right? That's what happens. Now, as this signal switches, it's called excitation contraction coupling. It's going to spread, so more and more muscle cells will contract. Okay? One more will. Okay, let's see. Okay. The electrical signal does not cause the contraction or the sliding of the myosin and actin. But the electrical signal does cause calcium to rise intracellularly, and the calcium allows the filaments to slide, because remember, the calcium makes the troponin, right? Makes the troponin. It's a protein that'll change its shape and pull that tropomyosin out of the way, right? So you must have normal blood calcium, right? 9 to 11, yes, you should know that, and such. And that allows for all of this to happen. Okay? Again, page, lovely graphic, figure 911, if you look at that. Basically, it just shows a sarcoplasmic reticulum, the calcium going out, and stimulating those, the contraction, okay? It just means that the signal gets spread to more and more muscle cells, okay? Okay, now let's talk just a little bit more about the cross bridge formation, okay? The cross bridge formation. Okay, there's a lovely graphic, figure 9.12, okay? You need to read these slowly and think about them after class, okay? Okay. Adenosine triphosphate, ATP. ATP, when it attaches to the myosin head, right, it causes a separation of the myosin head, okay, where it's attached, the cross bridge, okay? ATP causes that. It causes a separation. But then when you split off one of those phosphates, it causes the caulking for a split second. And that caulking mechanism is what attaches each time. Okay? And again, the separation is called by the ATP attaching. The splitting causes the caulking of the mechanism for a split second. But, you know, things that are spring-loaded, if you pull on them, that spring pulls it back, always, right? Yes? That's the way these myosin heads are. They always want to go back to their resting state, okay? And such. Okay. We talked a little bit about rigor mortis, right? When you die, you get stiff, yes? Why is that? You get stiff because when you die, you stop making ATP. And ATP is what unhooks the bridge, the cross bridge. Okay? So you don't get a separation. So you get really stiff as a board, right? Okay? That usually happens within 3 or 4 hours. Yes? And you've seen pictures of people in odd positions, right? And you can pick them up and they're stiff as a board. Yes? And that's called rigor mortis. However, what happens over the next 48 to 60 hours, 48 to 60 hours is those muscle proteins start breaking down, and so the bridges break, and you become loose again. You don't have the rigor mortis, okay? It goes away, right? Because those muscle proteins start breaking down, yes? Again, what's it take to make the cross bridge separate? ATP, right? And once that muscle is attached, once that cross bridge is made and you're not making any more ATP, it just freezes stuck together. But when you die, you stop pumping blood everywhere, you stop making ATP, then in time, the muscle proteins are going to break down and you get loose again. Okay? So. Okay. Muscle tension is the force exerted by contracting muscle. The load is the opposing force exerted on the muscle. Okay, right? So we have a little bit of muscle tension at all time in order to stand up, right? We talked about muscle tone. And if I go to pick this up, this is the load, right? My muscles are having to overcome the load, yes? Right? If it's a bigger load, right, then I have to recruit a lot more muscles to move that load, okay? Okay, real quickly, let's talk about a motor unit, M-O-T-O-R, a motor unit, right, is one motor neuron and all the muscle fibers it innervates. Okay? That's the definition of a motor unit. Motor as a motion movement, right? Okay? So one nerve doesn't just go to one muscle cell. One nerve can, here in my example, 1, 2, 3, but it may be 1, 2, 3, but it may be 300. Okay? Right? 300. Okay? It just depends. Okay? And we'll talk in a future chapter of neurology about a graded muscle response. Okay? Right? Okay? A graded muscle response is this. It just takes a little bit of strength to lift something light, but it takes a lot more strength to lift something heavy, right? Yes? Okay. So, men particularly, listen to me, Joseph, right? Yes? So, if I go to shake a lady's hand, yes? Right? We put a little squeeze on there, right? Yes? But men are real bad about it. Have you ever had this happen to you? They cramp down.
Yeah.
That guy right there, yes? Do not do that, right? Yes? If I shake Miss Madison's hand, then I'm going to squeeze very lightly. Hi, how you doing? Yes? But Joseph, I'm going to show him. Oh, man. Here, put her there, Joseph. Right? Yes? I'm going to give it to him. Yes? That's a graded muscle response. I am sending a lot more signals to a lot more muscles because I'm cramping down as hard as I can. Right? Yes? Okay? But I'm not going to do that. Don't do that to a lady. Mm-hmm. When you meet a lady, you go, oh, hi, how you doing, Miss Madison? Pleasure to meet you, right? Yes? Because it's very annoying to a lady to get squeezed, right? Real hard. Yes? So that's a graded muscle response. In this, I only do a little bit of muscle response, right? A little bit of muscles. But over here, I'm cranking down really hard on Mr. Joseph. Yes? Does that make sense? So when I am shaking hands with Joseph, I recruit more muscles, right? Recruit. Yes, you're in the Army now. More and more guys got to get in the Army. They're recruits. Yes? Right? So that is a graded muscle response. G-R-A-D-E-D. Graded muscle response. All right? A graded muscle response. Okay? Now, okay, let's talk about this. When they measure the electrical signal in a muscle, okay, let's say you get a big box on your front porch, yes? And you go to lift that box, and it's full of, I got 2 gallons of motorcycle oil the other day, right? And it wasn't a very big box, but I went and I'm like, oh crap, I didn't realize it was that heavy. And the first time I didn't pick it up, no. So I had to do it again. I had to lift again on it, right? So it took 2 tries, and the second time I recruited more muscle fibers because it was heavier than I thought, right? So each muscle response to each contraction, right? And because it was heavy, I recruited more fibers, right? And I got more signal. Yes? It's a graded muscle response. Yes? Okay? So what can happen though, too, is you can have, the muscle can be stimulated over and over and over and over and over again, right? But if you stimulate it too much, what will happen is you will get this. Okay? And that is said tetany, or a fused muscle contraction, right? You get so much stimulation that the muscle, the response will get stronger, 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 stronger until, right? Now, if someone is electrocuted, what do? Right? That's called tetany. Right? Oh, by the way, tetanus, right? Tetanus is lockjaw, right? You folks have never seen it, neither have I in my lifetime, because tetanus shot and some other things. But anyway, tetany is, right? But you get a hold of 440, right? You're not hard to come and loose, okay? Because you have such a muscle response that it goes, the muscle doesn't relax. Have you heard stories about they're in a car wreck and Dad gets out of the car and the car has rolled over? And oh, by the way, the car's on Dad's little girl, and Dad runs over there and grabs the car and lifts it up, and she pulls her leg out. Well, a lot of those stories are true. Why? Because tetany, right, can make people superhuman, right? Oh, by the way, people on drugs, the same thing. But anyway, tetany. This is called tetany, where you get, it's called fused or tetany, right? And again, I use the example of tetanus, lockjaw, okay? So where all these are fused together, you get one long continuous, right? Tremendous, okay? Fused or complete tetanus, right? Rigid, tense, no relaxation at all between stimuli, okay? Now, let's talk about some different types of muscle contractions, okay? Okay. Isometric. Isometric, okay? In an isometric contraction, what happens is this. I'll give you an example right here, yes? I take this hand and I put it against this hand and I push with both. And I push as hard as I can, right? Now, I'm developing tension in all these muscles, yes? Is my muscle shortening? Are my muscles shortening when I do this?
No.
No, they're not shortening. But the tension is going up, 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 right? The same thing, when I was a kid, they wanted you to do isometric exercise. You stand in the doorway, you push on the door frame. You push on the door frame this way, yes? Right? Yes? Or ladies would do this. You know why they would do that? No? Build up their pectoral muscles. Because what happens if you build up your pectoral muscles, ladies? Certain objects look bigger, right? I must.
Oh my gosh, I remember my mom saying.
Okay, right? Okay. So anyway, that's an isometric contraction. The tension goes up, but the muscle does not shorten, right? Yes? Okay. Isometric. Okay? Now, let's talk about the next one. It's isotonic. Isotonic, right? You get muscle tension developed, and the muscle changes its length. Notice I didn't say shorten, I didn't say lengthen. I said it changes its length, right? So the two types of isotonic are concentric and eccentric. C-O-N-C-E-N-T-R-I-C. Eccentric, right? Right? In concentric, that's what we think about. If I'm doing curls and I'm doing this, that's a concentric muscle contraction, right? And I'm shortening the muscle, right? Here the muscle tension develops and the muscle shortens. Okay? Now, if tension develops and the muscle lengthens, that's called eccentric. Okay, tension develops, but the muscle lengthens. Okay? And again, this is your calf walking uphill, right? Or the example I used, right? I put a new roof on my garage. I have the tools in the toolbox and I'm up there working. My son climbs up the ladder, and I hand the toolbox to him. Do I drop the toolbox on his head? No. Slowly, it was heavy. I put a metal roof, had all metal cutting tools in it, right? And so it's like, here you go. Yes? Right? That is eccentric, right? Joseph, you probably maybe know this. What do they call that where you do? Do they call it negatives or something like that in weightlifting? Okay, right? And the eccentric muscle contractions, for the same amount of force, you get more tension and you get much more DOMS, delayed onset muscle soreness, right? If you're shortening the muscle, you don't get near as sore as if you're lengthening the muscle under tension, right? That's why you run uphill a bunch and your calves are sore. Yes? Yesterday, got home from church, did the jump rope for 10 minutes, 3 3-minute rounds, and then a minute of speed work, right? My calves were kind of tired, and I ate lunch, and then I rode the bike around the lake, right? From my house down the lake and around, yes? And then, oh, by the way, I did a Bowflex later that afternoon. And so I did a Bowflex, and I do squats, and then I do calf raises with weight on my shoulders, see? Right? And so, man, I was tired by the evening, and the wife got home, and we had dinner. And then she said, oh, we need to go for a walk. So I went for a walk, and oh, my calves, all that work, right? Yes? But anyway, you need to know isometric, the muscle doesn't shorten or lengthen, but tension develops. Now, another example of isometric too is this, posture, right? Yes? When I stand up here, I have certain postural muscles that are always working. And they always have a little bit of tension on them to keep me standing up. If I did not have that isometric muscle contraction, I would look like this. Right? Yes? But I always have that, a little bit of that isometric muscle tone going on. Yes? Okay? And isotonic, the muscle's going to develop tension, but again, it may shorten or lengthen. If it shortens, this is normally what we think of, weightlifting, doing my curls, right? The muscle will shorten. And again, the eccentric, the muscle lengthens, but you get tension developed in it, okay? And you get much more sore doing the eccentric. Yes? Muscle tone. Even a relaxed muscle is almost always slightly contracted due to spinal reflexes. Muscle tone does not result in movements, but it keeps us standing up. Okay? Okay. Any questions about what we talked about so far? No? Okay. Again, make sure you get that. Isometric versus isotonic, and the two forms of isotonic, concentric or eccentric, because I will ask you questions about the difference. Okay? Yes? It's really not that hard. It's really not hard if you think about it a little bit. Okay? I always have to brush up on it because, I teach this 2 times a year. And I always have to brush up on that. But anyway. Okay? Now, let's talk about that. Let me find the page here. Okay. Let's talk about ATP in the muscles. Okay. Sorry, I got to draw a little bit right here. I got to make sure I get it all in. Okay. ATP stored. Okay. In our muscles, we have about 4 to 6 seconds worth of ATP stored, right? When I get past that, I have to do direct phosphorylation, right? Here we go. Creatine, creatine, creatinine phosphate. Okay, creatinine, ADP, ATP. Okay, creatinine kinase. Okay, and approximately, what's your book say? 15 seconds. 15 seconds. Okay, now let's talk about that. Okay, direct phosphorylation. Direct phosphorylation is this. Remember, I said an ATP molecule, right? If it's got two, it's adenosine diphosphate, and we want to stick another one on, so it's ATP, right? ATP, yes? Okay, so we have 4 to 6 seconds stored, but if I exercise longer than 4 to 6 seconds, I gotta make some ATP. How does the body make some ATP? The body makes some ATP next by taking a chemical, creatinine phosphate, right? Creatinine phosphate. And we have an enzyme called creatinine kinase. ACE means it's an enzyme, right? And creatinine phosphate gets its phosphate chopped off, and the adenosine diphosphate gets the phosphate added on, so the adenosine diphosphate becomes adenosine triphosphate. The original recycler of your body. The original recycler. But anyway, okay? And so we can do that, and we will make one molecule of ATP for each molecule of creatinine phosphate. And again, this is figure 919. You don't necessarily have to draw this, okay? Figure 919, right? So for 4 to 6 seconds, I got enough stored in my muscles. But when I get past that, 6 seconds approximately, right, I got to make some more ATP if I want to keep walking down the street. Okay? So that's the next system. Well, guess what? We exercise longer than 15 seconds. So the next system is the anaerobic pathway, ANEROBIC pathway. Okay? The anaerobic pathway. What in the heck does that mean? Anaerobic. An means not or without. Okay? Anaerobic. Aerobic is this. Have you heard of aerobics? Have you heard of aerobic exercise? Jog, 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 jog. That's aerobic, right? Yes? So, if I pinch my nose and close my mouth, am I going to jog very far? No, I got to have air coming in and out. That's aerobic, right? But the next pathway is the anaerobic pathway, okay? The anaerobic pathway, right? And that is glycolysis, 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 right? And glycolysis, we're going to talk a lot more about that in chapter 23, but let's put it this way. Pyruvic acid, right, and lactic acid are the byproducts, right? And I'm going to get 2 ATP molecules, okay? Now, let me explain this. Okay? When you're in a foot race, maybe you're running the mile, right? And you run 3 laps around the track. And then you run that half lap, right? And you're a half a lap from the finish, yes? Right? And maybe the pace has been really tough, and you're really sucking wind. But guess what? Right at the end, you have to turn it on, right? Your kick, right? Your kick, yes? Certain people have more of a kick than others, don't they? Right? Yes? 68 Olympics, yes? One of the guys I read, he said that I had a hard time keeping up with the fast guys, but I knew if I kept up with the fast guys, when it comes to the end, I can outkick them, I can beat them, right? Yes? That is the anaerobic pathway. That is glycolysis, sugar splitting, okay? I can split sugar, and I can make 2 molecules of ATP, and that'll give me energy to keep going. Now, can you run that way? Does your kick last a long, long time? No, it doesn't. No, it doesn't. For a short amount of time, you can turn it on, yes? Right? And some people are better at that, yes? I used to exercise with a friend of mine, an attorney here, right? And if it was, I rode a 100-mile bike race. He beat me by like 10 minutes, which is like 5 or 6 seconds a mile. But anyway, okay? In that big long bike race, he would beat me. Yes? But if we were doing a shorter race and we were closer and there's a sprint at the end, I'd always beat him, right? Because I had better anaerobic capacity, because I had the genes for that, right? Yes? And so I could turn it on. If we're at the bottom of the hill and we race to the top of the hill, I'm going to beat him to the top of the hill. In fact, I was running the Chili Hilly half marathon in March one year, and there was a guy, and we were running together, and you hit those hills, right? And I'd always beat him to the top of the hill, and then he'd catch up. And on the flats, he was a little faster, right? But when it came to those hills, man, I turned it on, right? Yes? But anyway, that's the anaerobic. It's anaerobic because it doesn't have to do with, it doesn't have to do with how much you're breathing. You don't need oxygen. That's what anaerobic means. You don't need oxygen, right? Okay? So that's going to last for, let's see what your book say, 30 to 40 seconds. 30 to 40 seconds, right? Okay? Now, think about this. People that run the 400 meters, yes? One lap around the track, right? It's a very fast race, isn't it? Yes? How long does it take? If you're pretty decent. Maybe a minute, right? Guess what? 4 to 6 plus 15 plus 30 to 40, guess what? That's mainly what you're dealing with, right? That's mainly what you're dealing with. You have your stored, you have direct phosphorylation, you have the sugar splitting, the glycolysis, the anaerobic pathway, okay? Right? You can turn this on for a very short time, but it'll go for a short period of time, right? But that's a fast race, only one lap, yes? When you go past that, then you have to go the aerobic pathway, right? The aerobic pathway. A-E-R-O-B-I-C, the aerobic pathway. Right? Now, if you're not running that fast, how long can you run? Huh? Well, how long's a marathon? 26.2, right? How long's an ultra marathon? Some of them are 75, some of them are 100, right? Western States 100, yep. Right? Yes? So, this aerobic pathway, yes, you got to breathe. Right? Yes? By the way, when you run the marathon, are you running as fast as when you run the quarter mile? No way. No way. But when you're running for miles and miles and miles, you're sucking in oxygen, you're making ATP, right? Yes? Okay. This is called cellular respiration. It happens in the mitochondria. Right? What are the mitochondria? The mitochondria are the powerhouse of the cell. That's where you make most of your ATP. Right? That is why you can run for hours and hours and hours and hours. Right? Because in every cell of your body, you got these mitochondria and they're making energy. Yeah, in the form of ATP. Okay? Right? And oh, by the way, you're eating the bars and you're drinking the shakes and you're running, right? And you're turning that into ATP so you can keep running, right? And you got to breathe. If you ever stop breathing, you stop running. That's what's going to happen, see? So, this amazing body of ours has some stored energy, but then it's got 1, 2, 3 different systems, right? 3 different systems for making more energy. And this system will last for hours and hours and hours and hours and hours. This one will last for 30 or 40 seconds. This one maybe 10 seconds. 15 if you add the 4 to 6. Okay? Right? So, this amazing body of ours has 3 different ways to make ATP. It's astounding, right? It's astounding, yes? Now, we're going to talk all about this in chapter 23. We're going to talk about Krebs cycle, right? And we're going to talk about glycolysis. And we're going to talk about oxidative phosphorylation, all in chapter 23. So I know you can't wait to hear that one, right? But anyway, just realize this. What do I need you to get out of this? Oh, we got about 4 to 6 seconds. Then we go to direct phosphorylation. What is direct phosphorylation? It's splitting that creatine, knocking the phosphate off and hooking it onto the ADP, so it turns into ATP, right? So the ATP can get split again and give us energy, right? Oh, by the way, what comes next? For 30 or 40 seconds, we can do the anaerobic pathway, right? The anaerobic pathway. It does not have to do with how much you can breathe. When you get to the end of that 5K, right? Yes? When you get to the end of that 5K, you turn it on 30, 40 seconds, right? Yes? XIT one year, I ran against, I couldn't keep up with I was early 50s, and I couldn't keep up with the boys' track team, but I could keep up with the girls' track team, right? And Sarah Smith, right? And right at the end, me and old Sarah Smith, we're running, and she was athlete of the week on the front page of the paper, the sports page. And I'm like, oh, you're athlete of the week. I saw you, blah, blah, blah. You know, we were talking. I could tell she was hurting a little bit, and I was hurting a lot because I'm way older than her, right? Yes? And so what happened was we got close to the end, and I said, Sarah, are you going to hurt me? And she wouldn't say anything. Sarah, are you going to hurt me? I said it 3 times, and she would not answer, which meant I knew she was going to hurt me, right? So we got close to the end, and what did she do? She turned it on. She started hauling. She went for the kick, right? She screwed up because Dr. Weld, each leg is this much longer than hers, right? And right at the end, you know what I did? I did this. She was right behind me. You know why I did that? I'm in front of you. She kicked too soon, right? Yes? That's what happened. So I beat her, but right at the end. Now, 6 months later, she had improved so much I couldn't keep up with her. But anyway, in that particular race, yeah, and then she didn't want to talk to me. It's like, I went over and said, oh, hi, how you doing? Anyway, it's not like she's competitive or anything, right? Yes? But anyway, see, she could only last 30 or 40 seconds, and she went too soon. Or she probably would have beat me. Same thing happened to me running a 5K. What was this guy? Andrew Valdez, right? I don't know if you know Andrew, right? That time he was a great runner, right? And right at the end, you know, we were running, and you know, the guy was keeping up with me, so I went faster. Well, he's keeping up with me, so I went faster. And he was keeping up with me, and I went faster, right? And he kept up with me. And right at the end, all of a sudden, here comes the kick, and he outkicked me. He did. He beat me by 6 seconds, right? Yes? And then he's standing there all proud of himself, you know. So I went over, congratulations, good job, you know. And I said, how old are you? He said, oh, I'm 26. I said, oh, cool, great. He said, how old are you, Dr. Webb? So I'm 52, you know, right? And only beat me by 6 seconds. But anyway, I started the kick too soon, right? I should have waited to the end. I could have outkicked him, but I had that strategy, yes? Oh, by the way, when I showed up to sign up for the race, the lady goes, oh, you want to sign up for the 1 mile walk? And I said, no, I'd like to sign up for the 5K, right? Oh, okay. That lady's standing on the finish line, and it's either me or Andrew, and we're running, we're looking out, and she's freaking out. Oh my God, this old man. Jeez, I can't believe that. I came this close to beating him too. But anyway, it's not like I'm competitive. But, right? So your body has these systems. It's amazing that it can turn on from this system seamlessly to this system, seamlessly to this system. Right? Yes? It's amazing. Right? It really is. So make sure you get that. Yes? And again, 1 molecule of ATP, 2 molecules of ATP. When you take 1 molecule of sugar and you split it all the way, you get 32, right? So, again, 1 molecule of ATP with direct phosphorylation, not very much. 2 over here with the anaerobic pathway. That's not very much. But here, you get 32 molecules of ATP. That's why you can go for miles and miles and miles and miles, because you're making a lot of ATP. Okay? Yes? All right, let's see, what's next? Okay. There's a figure 9.20. It's the same thing. It's the same thing, basically. There's a young lady running. Okay, just real quickly, right? When the muscle contracts, about 40% of that energy is used to do work, right? But about 60% of that energy is heat, released in heat, right? You go out on a cold day and you're cold, but you start running and it's not too long and you warm up. If it's a warm day, pretty quick you're going to start sweating, right? Whenever I do the Bowflex, I have to have a little fan blowing on me, right? Right? And I do it with no shirt on because I'm sweating because the muscle contraction. Because about 40% is working the muscles, but about 60% is giving off this heat, right? Okay? When we climb mountains, we usually start out cold with not as many clothes on because we know once we start going up that mountain, we're going to heat up pretty quick and we don't want to sweat. Sweat is the enemy. You don't want to dehydrate yourself, okay? Right? And again, where does the heat go? Again, we talked about that. I drew the thing, the real cool picture of my truck, right? Yes? Right? And so, remember, here's your radiator, here's your engine. You got the radiator hoses on the top and the bottom, right? The radiator fluid goes through the engine, gets hot, goes into the top of the radiator. Fan blows on the radiator, or you're just driving down the road and wind blows on the radiator. It cools the radiator fluid, it goes back into the engine, and it goes round and round and round, right? Yes? In our body, the blood is a radiator fluid. The blood takes up the heat, takes it to the surface. Our face gets red and hot and sweaty, and we give off that heat, and then it continues to circulate, right? So in our body, it's the blood that's the radiator fluid. Okay? Now, okay. Okay, how many of you know there are different types of athletes, right? Right? Yes? Now, how many of you know that, have you watched the Olympics before? Yes? You know what the weightlifters look like, right? Right? Yes? Do the marathon runners look like the weightlifters?
No.
No way, right? Because they're different types of athletes. Yes? Some people have the bigger, thicker muscles and they're powerful, right? Yes? Oh, by the way, when the athlete does the deadlift, does he do it 100 times? One time, right? But the marathoner runs 26 miles, right? Yes? Do swimmers look like weightlifters? No. Right? They don't. Yes? So we have different muscle fibers. And we have a different composition of muscle fibers, right? Yes? How many of you know some people are sprinters? They're fast. You can't hardly catch them, right? But does the sprinter ever win the marathon? No. Does the marathon ever win the 100-yard dash? No. Right? So we have different types of muscle fibers. And where does that come from? It comes from genetics. It comes from the combination. We all have all the different types of fibers, but most people are either like me, right? I have skinny muscle fibers, and they're really red, and I can go for hours and hours and hours and hours, right? But I can't lift heavy objects, right? Never have been able to, right? I'm not big and muscular, but I can outrun all those big guys, right? It's not a problem, see? But those big guys with the big muscles have a different type of muscle fiber, right? And they're strong, right? What was the guy's name? Mark McGuire and Sammy Sosa, right? Baseball, right? Yes, Mark McGuire, his arm's bigger than my legs, right? Pow! Hit the baseball, right? Boom, knock it out of the field, right? Yes? Now, could that guy jog a marathon? No way, right? See, those big muscle fibers, right? They don't need a lot of oxygen, and they, one or two times, very short. They fatigue very quickly, right? Whereas the long, skinny guy with the red muscle fibers, guess what? He can go for hours and hours and hours, right? Yes? How many of you know some people have fat calves, right? And some people have skinny calves. And the people with skinny calves are the marathon runners, right? Yes? Because those skinny calves, they can go boom, boom, boom for hours and hours and hours and hours. That's the way it works, okay? So let's talk a little bit about the muscle fibers, okay? The different types. Now, they're actually even classified more specific than this, but we're doing a general overview, okay? So, okay, the fast glycolytic fibers, right? The fast twitch fibers, okay? They're white or sometimes called pale, yes? And this is the weightlifter, right? And they're good for 1 or 2 or 3 times, but at maximum, but that's what they can do, right? On the other side, right, you have the guys with the red fibers. Yes? And they are the slow oxidative fibers, right? And these are the aerobic athletes, right? The marathoners. And these are the weightlifters, right? And then the middle, you have fast oxidative, and these are pink. Say red to pink. Yeah, red to pink. Red to pink, right? Red to pink, right? The color has to do with myoglobin. That's why myoglobin, have you heard of hemoglobin, right? In your blood carries the oxygen. Guess what? Myoglobin in your muscles. But anyway, okay, these are the sprinters. Okay? Now, your muscle composition is determined by genetics, all right? Yes? Your muscle composition is determined by genetics. Now, you can work really hard, and you can to a certain extent change this, right? If you're fast and you're a sprinter, and maybe you want to be a middle distance runner, or you want to be a miler, right? You can train, and you will improve. Okay. Back in the Olympics, Olympic athletes, I have a friend that's his junior Olympic coach, wrestling coach, right? But anyway, they stick a needle in their fanny and pull it out and measure the percentage of fibers, different types of fibers, and that tells you what they're going to be best at. Because some guys are sprinters, some guys are middle distance, some guys are endurance runners, right? Yes? But that's determined genetically, right? Okay? Okay. My climbing partner, right? I got a call into him tonight, right? Trying to line out a climb with him. But anyway, he is this much taller than me and he's twice as big. He's a big dude, right? And he's fit, right? But I'm just saying we have different type of muscle fiber, right? He's a big muscular guy. Who gets to the top of the mountain fastest? He's 20 years younger than me. I do, right? But if he collapses on the side of the mountain, am I going to carry him off the mountain? No way. He weighs 238 pounds, he told me one time, right? But I guarantee you, if I go down, Ben's going to pick me up on his shoulders and carry me off that mountain. I have no doubt, because he's a powerful man, right? Yes? He has some more. Yes, so he's not fast. Well, by the way, after about 8 or 10 hours, I'm dragging. I'm tired. I'm glad we're going down the mountain and we're not yet to the truck yet, and I'm dragging. He's like, come on, let's go. He's still going. He's still going. He's way younger than I am, but anyway, right? But if it's a foot race, I'm going to beat him. If it's short, I'm going to beat him, even though he's 20 years younger than me, right? He has different type of muscle fibers. He says, I'm a Clydesdale, right? You know what a Clydesdale is, right? The Budweiser horses, right? The great, big, powerful one, right? They're not fast, but they can pull anything. That's what he is. But anyway, yes? So, different people, different genetics, right? And you can modify that by training. You can modify that somewhat by training, but basically you get what you get genetically, right? It's like my son. I told him, I had that nose. My father had that nose. You have this nose. Guess what? Your kid's probably going to have this nose. It's just the way it goes. It's a Weld thing, right? Yes. Okay. And it's funny too. I have two sons. My older son is tall and skinny like me, and would be better aerobically, but he does lift the weights too. He's bigger and thicker than me, but my younger son, much more muscular, right? He can pick up heavy objects. Don't mess with him. He's a 215-pound ex-Marine. There's never an ex-Marine. He's a former Marine. But anyway, so don't mess with that kid. So anyway, okay? Genetics, right? The different things. Okay? Now, how about we just take a little break for a little bit? I need a break for a minute, okay?